Okay, so today we're talking about natural logarithms, and we've been working with logs all this week. Okay, and when you are working with exponential functions, some of this was review, so this might have been something that you guys highlighted when you have this natural base function, right? Y equals e to the x. That's the irrational number with an approximate value of 2.718. Okay, what we're going to focus on today is this natural logarithm. So one thing I hope that you highlighted here is the natural logarithm is the inverse of a natural base exponential function. Okay, I also think it's helpful to know that if you have log base e of x, okay, that is one way to think of it, but it is abbreviated as this is ln. I know the capital I in text often looks like an L, but this is L. So I always think natural log, it's just ln in reverse. I don't know why it's not the other way. Okay, and then you also read about how every point is reflected in this line y equals x. So I want us to label that on the graph. We know that if they're inverses, they're going to be reflections over this line. So we also did some graphs of log this week. Okay, the graph of a natural log is going to have that same shape. And if you have log base e of x, okay, we are going to write that as the natural log of x. Okay, and then this one is going to be e to the x. All right, now the next thing you guys read about was that you can write equivalent exponential functions using the definition. Okay, and they give you this example. The natural log of 6 is equal to x. Okay, and then the log of e base 6 equals x, and that is e to the x equals 6. Okay, so I know sometimes that is hard to process, so we're going to write this out in a different way. If you have the natural log of 6 and it is equal to some value, okay, we'll call it x. What this is telling you is the natural log is the same thing as log base e. This is what we talked about this week. So when you're going to write that in exponential form, you're already familiar with that process. Remember, you have your base, your answer, your exponent. Okay, so the base of the log is e. The exponent would be x, and it would be equal to 6. So that is going to be your exponential form. And you can go in either direction. So let's say you have e to the x is equal to 0.5 or a half. You can write that in log form by doing the log with the base of e. That would be of 0.5 equal to your value of x. When you're going from exponential to log, one thing I always tell myself to help me remember is that it's going to equal the exponent. So if x is the exponent, it's going to be equal to x. Again, we are not going to write the natural log like this. We're going to simplify it. So it's going to be the natural log of 0.5 equals x. Okay, so that is going to be your log form. So in log form, we're going to write the natural log of a half is equal to x. Okay, we've also been working with properties this week. So those same properties that apply to a log of base b are also going to apply to your natural logarithms. Okay, so we are going to be using the quotient rule, the power rule, the product rule. We're going to be using all of those today. All right, so based on these two examples that we just went over, I want you guys to try example 1. I want you to write each exponential equation in log form, and I want you to write each log equation in exponential form. Okay, just give it a try, even if you're unsure, that's okay. You can try things and make mistakes, and you can edit if needed. All right, let's see how we did for this first one. So remember, whatever you have here as the base of your exponent is going to be the base of your log. If you want to write the first step as the log base e, okay, of the value of 45 is equal to 3x, that can be your first step. But your final answer is going to be the natural log of 45 equals 3x. You don't have to solve for x here. All we're doing is writing this in log form. Okay, so this can be your final answer. Okay, so if you wrote it like this as your first step, we're just going to simplify. And anytime you have a base of e, you can automatically convert that to the natural log. Okay, so the base of e means you're going to have natural log. So instead of writing out the log base e, we can just write out the natural log here. Okay, now, when you have a binomial here, you have x plus 1, please double check that you are writing that in parentheses. It does mean something different if you don't have them. That would mean you take the natural log of x and then you add 1. This means you add 1 to x, then take the natural log. Okay, so we do need to have that anytime you have a binomial. And then it's going to be equal to the exponent. Okay, so as you're doing this on your own, this can be a helpful little note. It's going to equal the exponent. So equals 5 equals 3x. Okay, and then anytime you have a binomial, just make sure you put those in parentheses. Okay, little note to help you remember that. All right, do you need another couple seconds to try example 2, or are we ready? Ready to go? All right, Jack, what'd you get for A? What'd you try? Yep, e to the power of 2x is equal to 36. Okay, so then your base, your answer, your exponent. Your base is e anytime you have the natural log. Okay, so go ahead and do part B if you haven't already. Okay, and then let me know what you get for part B. Yeah? Yes. So your 3 zeros between the decimal. Okay, great. All right, so moving on to example 3, we're going to write each expression as a single logarithm. So that means you are going to only have one log, so 1 ln. So here, see how you have 2? See how you have 2 here? You have 2 here, okay? In your final answer, you're only going to have 1, okay? So to write each of these, we are going to use our log properties. Okay, so we have the power rule or power property. Okay, the quotient and the product. Okay, so when we were using the power property, we were bringing exponents in front. This time, we're going to be using the power property in reverse. Okay, so instead of having an exponent and bringing it in front, those exponents are already in front, and we have to write it as the exponent. So when you are looking at these, you are never going to leave a value in front of ln. All right, so let's do part A together, and then I'm going to have you guys try part B. So in part A, if you have anything in front, this is going to become an exponent, and then there's nothing in front there. So our first step, we're going to use that power property. It'll be the natural log of 3, and then this is going to become the exponent. So 3 to the third minus the natural log of 9. Okay, so we use the power property. All right, and then you can simplify here, or you can do that in the next step. If you have the minus, what property are we going to use? The quotient. Yep. So do you guys think you can write out the next step? Or do we need some help still? Or we got it? Or we don't. Okay, so we're going to do the natural log. Okay, so the quotient means now you're going to have a single log, right? Whatever comes first is going to be the numerator. So what's 3 to the third? 27. 27 divided by 9 is 3. Okay, and now we have this as a single logarithm. So this is our final answer. Okay, so you're using the quotient property, and then all we did was simplify. Okay, you guys try part B and part C. Do as much as you can for part C without your calculator. first step was pretty good. Okay, so cool. Tell me what you did first for B.
I don't know what I did. Oh yeah, I took the exponent. I put 2.
Yeah.
The exponent.
Great.
And then the same thing on that side.
Okay. All right. Great. So you do know what you did.
Yeah.
Okay. All right. Good work. So now once you've done that, okay, the plus means we're going to use which rule? So first we use the power property. What did you guys use next? If you had plus, what did you use? Yes, the product. Now I want you guys to double check this. When you are using the product property, okay, this is when you're going to condense it to one log. Okay, so I saw a couple of you still have like 2 logs when you did this step. So it becomes 1 natural log, and then you are going to multiply x squared by 4 squared, which we know is 16. Okay, so then your final answer is just the natural log of 16x squared. You can keep that in parentheses, or it is one term, so they're not mathematically necessary, but they are welcome, should you choose to use them. Okay, so go ahead and make any edits that you need to, and then I want you to start part C. Okay, so if we use part A and B to kind of help us with what we should do first, we can see that we use the power property. Okay, so we're going to do as much without a calculator as we can. Okay, I love seeing that you guys jumped right in and did the powers. That's excellent. Okay, I even saw that we did a nice job of distributing, right? So 1 to the 4th is 1, 3 to the 4th is 81. Okay. All right, now this, we don't want to do that without a calculator, so I'm going to have you think of this in a different way, okay? So a lot of things we've been doing thinking about different bases. So I want you to leave this as 9 to the 6th with right now, because we're going to do as much without our calculator as we can, okay? So we did our power rule, our power property. Then we simplified because we just distributed that exponent. Now we're going to use the quotient rule. So when you are using the quotient rule, now you only have 1 natural log. So it's 1 over 81 divided by 1 over 9 to the 6th. But when you're dividing fractions, we're going to multiply by the reciprocal. So let's see if we can write that out. All right, so then let's look at, sometimes just rewriting it visually can really help you guys connect some of these steps. Okay, so you would just flip that, right? All right, do you guys have any ideas on what we can do so that we don't have to use our calculator yet? Okay, yeah. We're going to do that in the next step. So with 9 to the 6th and 81, we know 81 is just what? 9 squared, right? Yeah, so like you guys said, we are going to be dividing that. So if we think of that as 9 squared, isn't that just the natural log of 9 to the 6th divided by 9 to the 2nd? Okay, so if you had to write an answer without a calculator, you would just do the natural log of 9 to what power? The 4th. Okay, which would really just be what times what? 81 times 81, okay? And I would not make you do that on an assessment without a calculator, 9 to the 4th. Or maybe I would, I don't know.
Don't give her ideas.
Shit. Don't give her any ideas. Okay, so sometimes it's helpful to just think of this in a different way. We're really just a couple months away from the SAT, so sometimes just reviewing some of these properties can help you think of this in a different way. Did I say SAT or did I say something else?
Well,
Okay.
some of us in here say.
Yes, SAT, PSAT, work keys. Yeah, the juniors do that. All right, now we are going to solve with our natural log. So on this page, do you see how we have the natural log of 45 was equal to 3x? I said you can just leave it like that. We're going to learn how to solve these for x. Okay? So repetition is good. So I know you've heard me say this a lot of times, but we're using logarithms to solve because they're the inverse of exponential equations. Okay, so we're solving the exponential with logs. And yesterday we used the common log to solve. So log base 10. Now, when we're using the base of e, we are going to use the natural log. Okay, which is ln. And we're going to be using that because that is the inverse. An inverse operation undoes, in this case, e, undoes the value of e. So you are going to isolate the base first when solving. Okay, and when we're saying you're isolating the base, what you're isolating is e to the x. That is your base. Okay, so you're also going to be solving equations that contain the natural log. So you're going to be given the natural log, and then you're going to have to solve. So for those, you are going to be writing the log in exponential form. Okay, so when you're doing that in exponential form, that means you would be given something like this. The natural log of y is equal to x. What you have to do is rewrite that. So it's e to the x equals y. Okay, so this is the exponential form. Right? And you know, I like to remind you that you have to show all your work. The reason why I am reminding you of that is because what I'm assessing in this chapter is your work with logs. Okay, so you're going to have to use your logs to solve. Okay, so your logs are needed. All right, so we're going to solve each equation. We're going to round to the nearest 10,000. Okay, something that you're going to have to do on your assessment is you're going to have to write each solution as an exact value and as a rounded value. So we're going to practice that. Okay, so we're going to write each solution. Okay, as exact and rounded. Okay, so for the first one we have e to the x equals 5.5 5.8. So it says the first thing we have to do is isolate. Well, this is already isolated. So once you have it isolated, all you need to do is take the natural log of both sides. Okay, so once that's isolated, you're going to take the natural log of 5.8. You're going to take the natural log of e to the x. And then we're going to use our power rule. So our power rule drops this x in front. So you have x times the natural log of e equals the natural log of 5.8. Now that is what we did yesterday. It's just we did the common log, right? We brought that in front. And then do you guys remember what we did next after we took the log? Yeah, we divided. Now, this is special because the natural log and e are inverses. So in your calculator, I want you to take the natural log of e. Okay, can you guys find the natural log button? It just reminded me of Dora the Explorer. Are you guys the Dora generation?
Yeah.
Can you find the big blue mountain? The natural log button? Great, you did it. Okay, so if you did the natural log of, and then if you want to use this E button above the division sign, okay, what do you get? Yeah, you should get 1. If you do the natural log and you do this one, okay, see how when you do e to the x, it gives you this? It's because e has to have an exponent. So e is e to the first. Okay, so what happens there when you take the inverse, that's exactly like when you take log base 2 of 2. Remember how that's going to be 1? That's one of our special properties. So if you divide by 1, you're just going to get the natural log of 5.8. So you can divide by 1, you just don't have to. Okay, and then we're going to calculate the natural log of 5.8 on our calculator. Okay, we're rounding to the nearest 10,000th, which is going to be 4 decimal places. So I have 75785, so that is going to be rounded up. All right, so now I want you to go to part B, and in part B, I want you to isolate e to the x. Okay, so your natural log button is right below your log button, okay? All right, and so we have to isolate e to the x. So Jack D, tell me what you did to do that. Great. Nice. Okay, so you subtract 3, you get 15. Divide by 5, you get 3. Okay, and then once you have this isolated, now you can apply the natural log. So when you apply the natural log to both sides, And you're going to practice this a lot. You're going to get in the habit of knowing, like, your next step is taking the natural log. So if you want to leave some space there, just like with the log, we want to write it on the left side. Because we know that this is going to be 1, if you guys just want to drop the x in front, and you can cancel those out because they're going to make 1, that is fine. Okay, so then you have the natural log of 3, and we're going to, again, round to the nearest 10,000. Okay, so for both of these, we found our 2 answers. We found the exact. So an exact answer is not rounded. It's going to be an expression. So the natural log of 5.8, that would be exact. This would be rounded. Okay, so on a no calculator section, you'd be asked to give the exact answer. On the calculator section, you'd be asked to find your rounded answer. All right, and then part C looks different. So A and B both have e to the x in them, right? Okay, what does C and D have in them? The natural log, right? So you don't have e, you have the natural log. So this says you're also going to solve equations that contain the natural log. You have to write these in exponential form. So that's what we're going to do with part C. Okay, the first thing we have to do is rewrite in exponential form. Okay, that is what you did in example 2. So I want you to look back there if you need a reference to write that in exponential form. Okay, if you want to go further after that, you can. I just want to make sure that you have that. Okay, and then once you have it in that form, you are going to be solving for x. Okay, and then Lorelai, will you tell me what you got when you wrote that in exponential form? Great, e to the third equals x plus 2. Okay, so for natural log, your base is e. Okay, and then remember, when you're writing this, whatever you have is equal to exponent. Okay, so if it's equal to 3, 3 is going to be your exponent. So now when you're solving for x, you just have to subtract 2 from both sides. Okay, so e to the third minus 2, that's going to equal x. And then we're going to go ahead and find that solution in our calculator. Okay, so this is the exact value. So the e to the x is above the ln. See how that works? They're inverses. Just like above the log is the 10 to the power, because they're inverse. Okay, and then you can just plug that in. Okay, so after the 5 is a 3, so this is going to stay a 5. All right, do you guys think you got the first step for part D? No? Don't look away from me. I feel like you guys got this. What do you think your first step's going to be? Yeah, you're going to use your product rule, your product property. So let's condense it to one log. Okay, so we're going to use our properties to write as a single log. Just a single log, sorry. In my head, I was thinking Beyonce's single lady. Oh, single log. Oh, single log. Put your exponents up. What do you guys think? We'll plan? All right, so once you know what rule you're going to use, so we talked about we're going to use the product property. That's going to be a single log. So I want you to write that down. Alright, so we should have the natural log of, okay, and then Cody, what did you multiply together for this? Yes, the 3x and the 2x. Okay, so don't forget to multiply the two x's together, so you have 6x squared equals 9. Okay, now we're at a similar place that we were with in part C. Anytime you have the natural log, you have to rewrite it in what form? Exponential. Did some of you do this part without me? Or did we get stuck? Yeah, you gotta write it with an E. Yep, so your base is E, so E to what power? 9 equals, yeah. Okay, so Nihal, what are we gonna do next? Yep, and then what'd you do after that? Exactly. So look, you just have x squared. We've been working with x squared, right? We know we just have to square root. Okay, when you take the square root, you have the plus or minus e to the 9th over 6. But you have the natural log. If you plug back in the negative, that's a problem because you can't take the log of a negative or 0. Okay, so when that happens, can't take the log of a negative. So the negative solution is, remember the word? Extraneous. Yes, good job. Okay, so then all you need is your final answer is the positive. Okay, so x is going to be the square root of e to the 9th over 6. That's your exact answer. And then we can calculate. So we have the square root of e to the 9th divided by 6. Okay, so that's your exact answer. That is your rounded answer. Oh, you can plug it in and check.
No, I mean like, how do you know it's not?
Well, if you have the negative, when you plug that back in, you can see if you have 3 times a negative value, that would give you the natural log of a negative. That's how I know it's extraneous. So if you plug this in, you can do that. You would just do it on your calculator. So like we are plugging it in just with mental math. Yeah, I think what you're asking is why aren't we writing out the check part, right? Oh yeah, we can do that too. So if you do plug that in, I recommend that you plug in this and not the rounded answer. So you can do the natural log of, and then this would be 3 times the square root of e to the 9th divided by 6. And then plus the natural log of 2 times, and then in the square root, it would be e to the 9th divided by 6. All right, moment of truth. What should we get? We got 9. Okay, and if you use the exact one, it will give you 9 exactly. If you use the rounded one, you might get 8.999 or 9.00 something. Yeah, so you can check it. I'm just not making you check these. Don't worry, we will be checking some other ones. Okay, and then for example 5, something else is going to come back that we talked about in chapter 7. Yep, the PERT formula. So Sarita deposits $750 in an account, paying 2.7% annual interest, and it says it's compounded continuously. Anytime it's compounded continuously, we know we are going to use the PERT formula. Okay, so A equals PE to the RT. So in part A, it says, what is the balance of Sarita's account after 3 years? Okay, so the first thing we're going to do is write out our equation, our model. We're going to be using that for all of these. Okay, so it's A equals, our principal amount is $750, that's what she invested. And then it's e to the power of 0.027, that's your rate, times t. For part A, they give you that the t is 3 years. So all we have to do is substitute that in. And then anytime it's money, remember, you're rounding to what decimal place? Yup, the nearest hundredth. Okay, and you can just write the times 3. Okay, so it's 0.278, so that does need to be bumped up to 28 cents. All right, and part B, it says how long will it take the balance in Sarita's account to reach at least 2,000? Okay, so if it's at least 2,000, all we need to do is find the value of t. Anytime it says how long, that indicates you're going to find the t value. So we're going to find t when the A equals 2,000. Okay, you can set this up as an equation. You don't have to do the inequality, even though it says the at least. Okay, so at the time of t, it will reach exactly that amount, and then anything more than that will be fine. All right, so when we're doing this, we're going to use the natural log to solve. Okay, so using our model, now it says this is the balance to be 2,000. That's going to be the value of A. Okay, 750 is still your principal, but now you are going to be solving for T. So just like we did earlier, you want to isolate E. So the first thing we're going to do is divide both sides by 750. Leave some space here because once you get E by itself, I'm going to be using that natural log. You don't have to divide and convert this to a decimal. You can leave it as a fraction. What I do if I notice that they both end in 0 is I'll divide those like that. I'll reduce it to 200 over 75 so I just don't have to write out as many numbers. And then once you have E alone, that's when you take the natural log. Okay, so we're going to take the natural log of both sides. Okay, and we're not going to do our calculation to the end. We don't want to round anything until the end here. Now remember, the natural log and E, those are inverses. So those operations undo each other. You could leave it as the natural log of E here, but remember that that's just going to be 1. So when you multiply anything by 1, you get the same thing. You're going to leave this as the natural log of 200 divided by 75. And then to get T by itself, we are going to divide both sides by 0.027. Okay, so that's going to be your exact value, the natural log of 200 over 75. Close that parenthesis, then divide by 0.027. Okay, so I want you to type that into your calculator. Okay, notice that the natural log is just of the 200 divided by 75, then we're going to divide. Okay, and then you're finding the time. This is in years. It doesn't say what to round to, so you can choose. I'm going to round to the nearest tenth. I just want you to make sure that you do put your units on there. Okay, so 36.3 years. You could do 36.33 years. That would be fine. Okay, if it doesn't tell you what to round to, you get to choose. All right, and then for part C, it says suppose she wants to have at least $1,000 in her account after 5 years. So she wants to have at least 1,000 after 5 years. And if the interest rate remains the same, what is the principal she should invest? Okay, so we're going to find P. I want you to see if you can set up that equation based on that information. Okay, so her account balance should be 1,000. You're trying to find P, so nothing should be plugged in there. Interest rate's the same, and it's after 5 years. Okay, again, it's fine if you use the equal sign here because it just has to be at least 1,000. And we are going to solve for P. So the first thing we're going to do is multiply 0.027 times 5. Okay, now if we want to solve for P, how how is P attached to E to the 1.35? Yeah, so if it's multiplied, then how do we move it over? Divide. So we're just going to divide each side by E to the 0.135. Okay, so 1,000 divided by E to the 0.135. Okay, so she would have to invest at least this much. At least $873.72. Okay, this is your exact value. This is your rounded value. Yep. All right, next work.